Good morning again. The next talk is about cogeneration in CFP plants. On the schedule it's indicated that the talk is by Professor Papanikolas, but because he had another engagement, myself and Aristides Bonanos will be co-hosting this presentation. So I'll give a brief introduction and talk about cogeneration mode with desalination, and then Aristides will present cogeneration for built environment applications. So just to give some context, the main thing we need to understand is how a power block works and how the losses are. So we introduce some kind of heat into the system that causes water to evaporate into steam, and then we can go through a heat exchanger to drive a steam turbine. The steam turbine is, of course, something that will remove enthalpy from the system that we have introduced in our initial stage and give electricity as the output. And then the cycle is closed by condensing the water, in this case, which is the working fluid, and the cycle is repeated. Now, of course, in a solar plant, we don't use, in the furnace, we don't use fossil fuels, but we replace that heat input with solar energy. Also, I mentioned yesterday Carnot efficiency, which is shown on the bottom. It's what governs the efficiency of these systems. Basically, we want to get as large of a hot temperature as we can as possible to improve the efficiency. But the efficiency implies that some energy is lost, and that energy is lost in the form of heat. And we can see what many of the energy conversion processes that we have and what their efficiency is. And when we see processes involving steam turbines, which is traditionally used for electricity generation, we have efficiencies of 40 to 50%. Other processes, depending on the temperatures at which they operate and the form of energy which they use, can have higher or lower efficiencies. For example, ocean thermal energy is a very low energy source, so it has only a 1 to 3% efficiency. But when we consider mechanical to electrical conversion, such as a generator followed by from the steam turbine, they can have very high efficiencies. And this is important because this is a picture of the energy flow in the United States in 2008. On the left are all the various energy sources that were used, and on the right is the product that's given. And what we see on the right is that this number is waste heat rejected to the environment in a percentage. It's 57% of all the energy used was rejected to the environment in heat. So the whole concept of cogeneration is to kind of harness this energy that's rejected, use it to produce something useful instead of just dumping it to the environment. Now, we need to kind of also understand the temperature at which various processes work. So obviously the energy that's rejected to the environment is rejected because it's of a lower form, a lower exergetic content. So it can't be used for electricity production, but there are other processes that it can be used as. So we need to kind of order on a temperature scale from cold to hot our processes and see where we're rejecting heat and how we can use that heat further on. So for example, starting from the high range temperature, there's thermochemical processes that were mentioned earlier by Luca. Then going down in the temperature scale, we can go to gas turbines, Brayton cycles, or steam turbines, or piston engines, or other process heat applications that we're going to talk a bit about, or desalination. So we can range in temperature from ambient all the way up to 1,000 or a little over 1,000 degrees Celsius in our processes that we have to get useful energy out of the system. So one of these systems that uses a very low-grade heat is a thermal desalination cycle. Now people have considered coupling this with solar plants in various capacities, and actually in next week you will have many more lectures on solar energy plus desalination. But some of the ways to do this coupling are indicated here schematically. Either you can use only the heat from the process, so the solar field will give heat to a desalination process. Some supplementary electrical energy will be used, and then we can produce water and power in a cogeneration scheme. Or we can use all the heat to produce electricity, and then take that electricity and use it again for a desalination. Or we can kind of combine the two and use both the heat and the power in a true cogeneration sense to drive, again, a desalination cycle. And that's the concept that we have followed in the Proteas facility, which you will visit on Friday. Basically, we have the solar field, which will give heat directly to the thermal energy storage, and from there we can drive both the power block and the thermal desalination system. And what we find is that, in fact, the coupling of these two processes in an integrated desalination cycle, an integrated process cycle, leads to improvement in efficiency overall of the plant, precisely because we are not dumping all that waste energy to the environment, but we're using it to generate another process. So in order to come up with that schematic, we made a full detailed model of our processes that we have at the facility, and this kind of complicated diagram on the right shows all the energy fluxes and energy flows that we have from the various stages, from the solar field to the storage to the power block and to the desalination cycles, and how this waste heat flows from the high enthalpy, high energy sources, high temperature sources, to the low temperature processes. Again, in the Proteas facility, the technologies that we use are heliostats and central receiver for the solar harvesting, molten salt, thermal energy storage, and then we have in parallel a power cycle, which is basically a steam engine, and a thermal desalination unit. And the idea is to use this energy, which is indicated as lost to the environment, but take it and introduce it to the desalination unit, and this is how we get a coupling of the two processes, and again in the overall efficiency of the plant. So again, some of the technologies that I mentioned, we have the heliostats. This is a schematic, a picture of our receiver before it was installed, the thermal energy storage, our heliostats, and the desalination unit, just very briefly. Some other technologies for cogeneration that have been used, I basically stole these slides from commercial companies. What this company specifically is promoting is the concentrated photovoltaics, which require a low temperature to operate. So what they do is they get a 15% efficiency from the photovoltaics themselves, but then they cool the photovoltaic panel in order to yield also hot water, which can be used in a domestic environment or in a hotel, and they have a commercial product that they have generated. Another interest in commercial product in cogeneration is what's called enhanced oil recovery. So oil fields are basically the oil is very viscous, so in order to improve the viscosity and enhance the pumping capacity, the oil needs to be heated up. So another company, GlassPoint, has developed solar fields precisely to yield process heat for this enhanced oil recovery. So they have an enclosed solar harvesting plant, enclosed because it's typically in desert environments and they want to avoid the cleaning from the dust falling on the mirrors. And they generate steam that is then pumped underground and used for the enhanced oil recovery. So that's kind of a very brief overview of cogeneration with desalination, and now my colleague Alaric will present about Fresnels and cogeneration.